Let me just start by, I suppose, a bit of an overview of where mobile industry is heading. Most of you would have seen this or different incarnations of some of these diagrams here. But I suppose one of the biggest or the first initiatives trying to imagine what a 5G enabled world would look like was this alliance called the NGMN, the Next Generation Mobile Networks Alliance. And they came together, operators came together and wrote a white paper back in 2015, which is where that triangle that you can see in the picture comes from, which is pretty much saying that we want to be more than just, if you like, internet access providers from a mobile perspective. We want to be enabling a myriad of future services for different industry verticals. And as you can see there, I won't go into too much detail. You can read the paper. There is a link on the slide. But in essence, anything to do with machine type communications, supporting millions of machines per square kilometer potentially in the future. Also, what they call mission critical communications, which would require potentially below 10 millisecond latencies to be delivered for certain use cases, and ultra high reliability in order to support both those, and of course continue to support the speeds and capacity required for mobile broadband communications, especially driven by video. So that was the ambition that was set by the NGMN white paper. Effort across industry to expand it space to use cases and revenue sources that I was referring to earlier. So I think internet access on being having the flexibility to address the pictures in the diagram, but it ranges from the healthcare scenarios like remote diagnostics, for instance, all the way to things like remote control of autonomous drones, smart cities, smart logistics, supporting energy industries and emergency services teams. As I said, industry has made a lot of efforts within the standard studies. The third have made an awful lot of effort in finding technical specifications for that. We need a rich ecosystem that comes together the devices and the applications and the open architectures and innovation can actually make all this true. So we're thinking that now we have a time where research and innovation is as important to take our industry to where we want it to be in 5 to 10 years' time potentially. If I move on to the challenges I suppose that we face are any chart that you look at, whether it's historical data or potentially forecast data, which is that the data volumes over the mobile networks are only year by year. The chart on the left side that comes from the mobile consumption in the UK has increased 4 times on average. Likewise, on the right-hand side, this is a forecast by Ericsson on the global of mobile traffic, and this is saying that effectively the increase is actually going to be even faster in the coming years with the emergence of 5G and new use cases. If I move on to the next slide, oops, I'm not. Sorry, just to reinforce the point that we need industry and the mobile industry in particular to achieve both significant cost reductions as well as the ability to support new services for increased revenue sources. Let me just step back and try to see if I can, I suppose, set the scene to see if sorry, I'm going to turn off the video because I'm being told that the audio is a little bit choppy, so I'll stop the video now just to allow for more of my voice to come through. Hopefully that works better. I was trying to explain that mobile network architecture today is characterized by a number of things. One is that it's highly hierarchical and pretty much centralized. So the core network nodes that you can see on the right-hand side sit typically in a handful of sites across the entire country. This, of course, depends on the size of the country. If you go towards the left-hand side, of course, the number of aggregation nodes increases with the next level of distribution all the way to the antenna sites and the base stations. And I will explain why that is important later on when I talk about the future, what the future mobile networks will look like. The next characteristics of the current mobile network architecture is that our mobile core network elements are pretty much hardware-based solutions where a single entity, like a mobility management entity or a packet gateway, will be effectively tightly integrated with a piece of hardware on some sort of monolithic solution from a single supplier. And I will explain later why that is important as well and how things are moving on in that space. The next key characteristic, moving all the way to the left-hand side of the picture, is that our cellular deployments are mostly macro cellular-based. We are starting to see small cells emerging and infill solutions, especially for hotspots and high-demand areas, but there is a long way to go for the types of density and small cell deployment that we expect to see in the future. The last characteristic of today's networks is, again, that also on the radio side, our solutions are fairly monolithic. And what we mean by that is that the baseband units and the radio units and the processing capacity required to schedule the resources for the radio network all come from a single network on what we might call a black box solution. And again, I will explain later how we're influencing industry to move away from that. If I now move on to what our target architecture looks like, as you can see, is quite different from the previous picture, and I will try to highlight the elements where it differs. The first one is that rather than being hierarchical and highly centralized, we expect the compute capacity to be highly distributed so that we can make dynamic use of compute resources and capacity when it's needed and where it's needed. The second one is the need for our transport network to be highly programmable so that as we use compute capacity from different parts of the network, the connectivity between those compute resources can be dynamically reprogrammed to provide the capacity, the speed, the quality of service, or whatever characteristics a particular service requires. The third one is the virtualization of the network functions. As I was explaining earlier, today, so traditional solutions have mostly been hardware-based, which means that the hardware solution and the actual function come from a single vendor. In the future, what we are expecting is more and more functions, and this is starting to happen today in most operators' networks. Network functions will become software components that can be dynamically deployed on general purpose compute hardware platforms. The fourth area where our ambitions differ from today's architecture is that we want to push the architecture to be a lot more open, with open interfaces between the different components and highly disaggregated architectures. And I will come back to that later and explain why that is important. And the last piece, which I will come back to later on, specifically in areas like radio, is how we see artificial intelligence playing a key role in the way we manage our networks in the future, to the extent where we are expecting networks to be increasingly automated end-to-end, thanks to the emerging AI-driven technologies. Now I will move on to a bit more specifics on the radio access network technologies and some of the key challenges that we need to overcome. These are not new challenges, but they are increasing as I said earlier, the capacity required is increasing, and also the flexibility that we require to serve all those different services increases as well. On the one hand, you probably all know that the radio access network is pretty much bears the highest cost base in a mobile operator's network. The actual percentage will depend on a specific operator's network, deployment model, but as a rule of thumb is pretty much bigger than the rest of the operator's network costs combined. The second big challenge is that, as we all know, spectrum is finite. And yes, new bands are starting to become available, especially in the high end of the spectrum, in areas like millimeter wave. However, as we all know, those suffer from significant challenges like propagation challenges, as well as obviously coverage and the requirements for line of sight visibility for them to be usable. I will come back to some of those challenges and how we're exploring ways to overcome them. The third one is the high dependency on the physical environment, and this is pretty much the channel between the antenna and the end device. And again, we are going to come back later to some of the ongoing research to try and help with that particular challenge. And the last one, as I've mentioned earlier, is that service differentiation is increasingly key if we want to target all of those new use cases that industry aspires to provide. One of the first areas where we are actively exploring and pushing industry towards our target architecture is the disaggregation and the virtualization of the radio access network. This means that, as I was saying earlier, what has traditionally been a single vendor, you might call proprietary radio access solution, where the antenna, the baseband, and the management plane would be all provided by a single vendor. We want to move to a fully disaggregated model where we can effectively split up the functions of a base station from the radio unit onto a distributed unit, which can be separate from the centralized unit. And we have an important element called the Run Intelligent Controller, or RIC, which I will come back later, as well as the management plane, which can also come from a different vendor and be deployed in a bit different part of the network. This disaggregation provides two main advantages. One is the ability to introduce smaller suppliers, new entrants, smaller vendors who might be dedicated to one of these layers, if you like, in the architecture. So we no longer need to procure our entire systems from the same supplier base, but we can introduce innovation in different parts of the architecture. The second key advantage is that these units can actually be located in different parts of the network. I was explaining earlier how we expect our network to become more distributed and the compute capacity being distributed across the network. So you could envisage having your centralized units for multiple base stations co-located at a particular site, which can bring specific optimization and efficiencies in the way we could actually share that platform across multiple base stations, and also share the processing capacity required to do things like scheduling or pre-coding across multiple base station sites. There are a number of opportunities where we are already exploring the use of disaggregated architectures, such as BT's neutral host solution, which is currently being trialed, which leverages a lot of the elements of this architecture to deliver indoor capacity solutions for multiple operators, where more than one operator can actually have virtualized radio solutions on a common compute platform. The second key area of research I want to highlight is the application of artificial intelligence to the way we run our radio networks. At the end of the day, what we want out of our solutions is more and more optimization of our radio resources, because, as I said earlier, they are finite and they are very expensive, both to deploy and run, but also being able to offer differentiated services. Just to run through a few of the use cases and the examples where we firmly believe that artificial intelligence and machine learning in particular can help us address those challenges, are things like nonlinear algorithms for pre-coding and scheduling, where we believe that the potential for massive MIMO to deliver much higher spectral efficiencies than what we have today is entirely possible. The top left diagram shows some of our current assumptions, under certain current assumptions, what is our expectations to the increased opportunity for using optimal pre-coding, which is the purple line at the top, versus the types of spectral efficiencies we're getting from today's MIMO systems. And as you can see, there is an awful lot of opportunity there by improving pre-coding and scheduling algorithms, as we said earlier, we can actually get a lot closer to that target spectral efficiency that we can see there. Closely coupled with efficiency, again, and optimization is the ability to apply machine learning to things like smart interference management, to optimization of broadcast beams. It can also be used for channel estimation and detection, and it is increasingly being looked at to manage the way we manage energy more efficiently on our base stations, which again is suboptimal today. Another key area, which is closely coupled with the use of AI and some of the techniques and the areas that I've mentioned earlier, is the evolution of radio architectures. There is an awful lot of literature out there and a lot of work in the research and academic environments in the evolution of today's networks, which are highly centralized. Effectively, one antenna is serving a particular cell and a particular area, moving all the way to what they call distributed massive MIMO is one of the generally used terms, where we're expecting cooperative pre-coding to enable us to form service clusters to simultaneously serve users from more than one antenna site. As you can see in that diagram, the three pink antenna elements from each of those could actually be used by cooperative pre-coding to serve a particular user. Going even beyond that concept, there is the concept of user-centric, cell-less massive MIMO. And that's going also using distributed massive MIMO techniques, but in this case, a particular user could be served by three antenna elements from three particular antennas, and a separate user could actually form a different cluster of different antennas. So in a sense, we're moving away from cellular systems whereby every user within the coverage area of a cell will be served by a particular base station, onto a much more cooperative environment and dynamic environment where users can actually be dynamically served by a different cluster of antennas. Of course, there are significant challenges to be addressed in order to achieve that goal. In particular, what the requirements of the front haul network to enable this massive cooperative system to work correctly. Another very interesting area of research that many of you may have heard of is the area of intelligent reflecting surfaces. In essence, what they are trying to overcome is the ability to reflect signals using a diffusely reflecting elements, which could be, for instance, placed in the facade of a building, which could be used to reflect signals in a particular way and in a particular direction. In particular, what is being looked at is how, if you look at the area of active reflecting surfaces, you can change the state of those antenna elements, or those reflecting elements in this case, to actually decide. You could be changing the phase or any other characteristics to actually form a beam towards a particular user, or direct a signal towards a particular user. And again, this is in tight coupling and cooperation with the main antenna. And of course, you can then achieve much further coverage and be able to reach your users much more effectively. Now, obviously, challenges again that need to be overcome is to enhance our channel estimation abilities, and of course the protocols for information exchange and phase tuning. And again, we strongly believe that AI is an area that can help us overcome those challenges. But the size of the prize is the extension of the range and obviously the expected improvements in spectral efficiency and how much capacity we can deliver with our radio networks. In the interest of time, and because I'm sure that you heard a lot about quantum computing, I wasn't going to talk about this in too much detail, but there are probably two areas where I would like to just point that, again, quantum computing can also be very relevant to wireless networks. On the one hand, the use of atomic clocks to massively increase the ability to synchronize multiple antenna elements, and in particular in distributed MIMO systems, as we mentioned earlier. This is particularly important because there is an increasing need to have tight synchronization between highly distributed antenna elements. The other key area for us in, again, a mobile or a wireless environment is the ability to exploit quantum computing for network automation purposes, which, as I said earlier, is one of our ambitions for the mobile architecture. And I just wanted to close the presentation by saying that the size of the prize, the types of services that we're trying to achieve are well beyond just cost savings or trying to deliver more traffic to our customers. As I said at the beginning of the presentation, mobile industry has an ambition to address many different customer segments, many different vertical segments. You can see here examples, and we are very active in many of these. Smart agriculture being a key one, health, as I mentioned earlier, whether it is remote diagnostics, whether it is health monitoring, whether it is IoT enabled health, is another key area of interest to BT. And I'm not going to go through the entire list here. I'm sure a lot of these will be familiar to you. But I just wanted to leave my section by saying we have great ambitions, but also great challenges ahead of us. And we're convinced that the research community, most of you in this audience, are key to make that happen. Thank you very much.